Wow, this is an amazing view, so let's get started. So I'm Max Weber, and I'm a Clojure developer at do.net. Do will bring you the paperless future by reinventing paperwork. Visit our website to learn more about our vision. At Do, I'm responsible for our Clojure team and the architecture of our cloud system. Today, I'm going to talk about event sourcing and how to combine it with the simplicity and power of Clojure. Therefore, I'm also going to explain the differences between event sourcing and the current state approach. The current state approach is the traditional way of modeling application state that we all know. After this introduction, I'm going to show you some ways how to implement event sourcing in Clojure. Then, I'm going to present event sourcing in a wider context, and you will learn something about the CQRS architecture approach, which is often used in combination with event sourcing. Last but not least, I'm also going to introduce you to the new open source library Eve, which we have started to extract from our code base to help other people to do event sourcing and CQRS in Clojure. I'm going to answer all your questions at the end of this talk. So, let's get started and talk about the motivation for using event sourcing. Maybe we should start at the most general perspective, the business side. Let's take an online shop as an example to explain why event sourcing is useful. So, here's the scenario. You start your shopping tour and put a Clojure book into your shopping cart. I don't know. The online shop have really everything on offer, so you also decide to order some more tea. This could be one possible model for the shopping cart which contains our chosen products. The data could be stored inside a document database, or maybe it's just a view on some relational database tables. However, the point is it represents the current state of our shopping tour. So, let's change our scenario a little bit. We pretend that our customer put the Clojure book and the tea in his shopping cart like in the first scenario. But now our customer thinks, oh, I still have enough tea, maybe I order some more next time. Therefore, he removes the tea from the shopping cart. Now, the end result would look like the following. If you look at the data, you will see that we have lost a valuable piece of information. The customer had Earl Grey tea in his shopping cart and probably has interest to buy this product in the future. Therefore, you have also lost a competitive advantage on the business side, since you are not able to increase your sales by recommending the Earl Grey tea the next time the customer visits your online shop. As a developer of the online shop, you can of course implement such a recommendation system which tracks the items of a shopping cart. But this kind of tracking, or rather state keeping, is not well supported by a current state architecture, since it is very different from a normal state, current state model. You also have to implement the tracking first before you can collect the tracking data and use it in your recommendation system. By using event sourcing, you can avoid this information loss, even in the case of future requirements which are not so foreseeable, like a recommendation system for an online shop. Especially when you analyze your historic data to learn more about the behavior of your customer, you get a lot of competitive advantages. Since with event sourcing, you have all the necessary data to answer questions like which product is removed from the shopping cart most often or replaced by another similar product, or is there some pattern that our checkout process is often cancelled at step 3. So, let's take a look at an example how this online shop example can be modeled with event sourcing. So, here we have two maps which represents the event that a product has been added to a particular shopping cart. Both refer to the shopping cart ID and the corresponding product ID. We have used the underscore event entry here to define a name for an event. The event name is a keyword with a namespace here. These events would reflect our first online shop scenario. So let's add another event to also model the second scenario. Here you have another event which states the fact that the customer has completely removed the Earl Grey tea from his shopping cart. In comparison to the current state approach, you don't lose any information here. However, in the end, you would need to know what the online shop customer has ordered when he do the checkout. So we need to build the current state for the shopping cart from the events somehow. The obvious function to transform a collection of events into a single value is reduce. The event sourcing functions of the Eve library offers some convenience when it comes to writing and combining functions which can be used in a reduce to derive the current state from a sequence of events. Here is an example. Here we define the events. These are the events we have already seen, plus an event which simply creates the shopping cart. And we will simply put it into a vector. Oh. So here we have another function which is a so-called event handler. Here you have the function signature of a model which is modified and something which continuously changes. So you put all the events in it to use this function inside a reduce call. This function merely only does some housekeeping and takes care that the correct quantity of a product is stored inside the shopping cart current state. So here's another function which handles the shopping cart remove command, and it simply removes it from the items in the current state model. So here you see some functions of the Eve library which helps you to combine those functions and then use it in a reduce to derive the current state, as we will see in a few seconds. And there's also some helper functions like this one, which simply helps you in the common case that you have to transfer the data from one map to another map, which is often the case because you transfer the event data into the current state model all the time. So here we invoke our shopping cart model function with a reduce and start with an empty map and our predefined events. So as you can see, this is the current state of our second online shop scenario, and we have derived it from our events. So, but this is not the only thing you can do. You can also rederive a historic state. So this one is the state of the first shopping cart scenario. We simply drop the last event, and therefore the remove from the shopping cart gets removed, and so you still have both products here inside this current state mode. So this is another possibility to use the reduce function to update an existing state with new events. This is also called a snapshot technique. So here we have the current state of our first online shop scenario, and here we simply apply the last event of our event list to the existing state, so that we simply receive the current state of our second online shop scenario. At first sight, the event sourcing approach may seem technically more complicated than the current state approach, but you will see that almost everything becomes easier and more flexible with event sourcing. The reason for this is that capturing the state in the form of events is simple, while the current state complex several concerns. As you can see here, an event captures what has happened at a given point in time in one value. These are our events, which we have already seen in this slide before. So for every given point in time, there is a separate value. The current state on the other side, here above, complex all these values. The previously described information loss is only one of the consequences. Another one is that you only have this single model, or rather view, on your data. Consequently, it is often the case that the model is used to implement different requirements of your system. This leads to the tendency that otherwise independent concerns of your system are often complected through the model of current state. With event sourcing, you are able to generate models out of the events which are adapted to the specific use case. So, I guess everybody inside this room knows which benefits you can leverage if you can use immutable data to solve your problem at hand. In comparison to the current state, an event is immutable. So, to perform a change in a system which uses event sourcing, you append a new event to the existing events. This is also exactly the case in our online shop event sourcing example, the previous slide before. So, an event should never be modified. Even if you have found a bug inside your system, you would emit new events which compensates the effects of the bug. In this way, the event shows exactly what has happened in your system, and you get an audit log for free here. This property, that every state change in your system is always represented by an event, also helps you in other cases. So, normally in an integration test, you check what your system has done. With the help of the events which has been emitted by your system during the test run, you are also able to check what your system has not done. This is particularly helpful for developing things like financial trading systems, for example, where a wrong additional action can easily cost you thousands of dollars per second. Even if you only implement a small separate recommendation system, you can use the events from the online shop system to see what has happened. So, you can continuously read the events from the other system and apply it to your system. For example, if a product is not longer offered in your online shop, the recommendation system can read the corresponding event from the online shop system and take care that the affected product is not longer included in any future recommendations. Having only the current state, the recommendation system has to synchronize its whole product table with the one of the online shop system every time. So, let's get back to the data of the events on this slide. I hope it's not too small. So, as you can see, every event includes an ID of the shopping cart here and an underscore position entry. So, what's the reason for that? From Clojure's time model, we have learned not to complete an identity with a value. While only having a single value in a Clojure atom or ref, you have one value for every given point in the case of event sourcing. For that reason, you have to make the identity and the notion of time explicit in the event value with the position and the identity entry. For that reason, you have to make the identity and the notion of time explicit, and to check what the causal order of the events is and which identity they refer. So, in the case of our shopping cart events, you have to know that the Earl Grey tea has been added to the shopping cart first before it has removed from it again. For the notion of time, we use a logical clock here, which is a simple counter that is incremented on every new event. Here, it is stored inside the underscore position entry of the event map. But you also need to know on which shopping cart the event has happened. So the shopping cart entry refers to our shopping cart from our previous examples. In the next section, I'm going to compare a more traditional architecture with an architecture where event sourcing is used. Also to discuss further points where the current state complex different concerns. Okay. This picture shows a traditional three-layer architecture. The domain model, or rather its schema, is often used throughout all the three layers. If you don't have a data-centric programming language, the data of the domain model objects is mostly converted a couple of times. Database table records become domain objects, which are converted to DTO objects, so that they can be used in the front end. And all of these things go the other way around when the user makes a change in the front end. However, even if you use pure data for this, the point is that the schema used for the data is almost the same throughout all the three layers, as I've already said, while the data is used for very different tasks. Therefore, it is also more likely that you end up with a complex solution, since your logic for the different tasks is somehow compacted through the shared schema of the used data. The most different and elementary categories in which types of tasks can be divided are read and write operations, despite the fact that read and write operations are fundamentally different. In most of today's applications, the same model is used for the read and for the write side. But these two categories have almost complete different requirements. The write part is all about keeping your data consistent, or rather make changes to them with asset guarantees wherever it is possible. When you read your data, you care more about nice query capabilities and short response times, for example. Sometimes it even doesn't matter if your query result doesn't yield the current state of your data. Think about a weekly updated sales report, for example. The read and the write side normally have other scaling challenges too. If you consider a typical application, you will most often observe that the read count outweighs the writes about at least one magnitude. So, if you do not intertwine your read and write operations, you are able to scale them independently from each other. In this way, you can utilize the fact that it's a lot easier to scale read operations than consistent write operations. This idea of the separation of the read and the write side has already a name, CQRS. So, CQRS is the abbreviation of Command Query Responsibility Segregation. So, commands are write operations and query are read operations. The CQRS term has emerged from the CQS definition, which only describes the separation of commands and queries at the object level. CQRS apply this separation on the architecture level of a system. Furthermore, it's often assumed that event sourcing is used at the heart of a CQRS architecture. In the next part, I'm going to give you an overview of a typical CQRS architecture. The following picture shows an illustration of a CQRS architecture. The architecture illustration demonstrates the separation between the command and query part very nicely. There's one application point for the commands and another one for the queries. So the query side is easier to comprehend than the command side. Therefore, let's get started with the query side. The query endpoint is merely a thin wrapper around some query statements for your database. In comparison to a traditional application, it stays a very simple component here, since it is not compacted with a domain model or any other write concerns. Due to the fact that the data of the query side is only used for reading concerns, it is also called read model. In the introduction, we have seen how to derive the current state, or rather read model, of a shopping cart from the given events. We have also learned that this is not the only read model we can derive from the events. So the database, here, the read model database, usually contains several different read models which are derived from the same events. In a CQRS architecture illustration, you see also a component with the name event bus. This component is responsible to dispatch the events which are the result of a command operation to the so-called event handlers. An event handler, on the right side, knows how to update a read model with the data of a new event. In our online shop scenario, there would be one event handler that updates the read model of a shopping cart on the basis of the incoming shopping cart events. It's important to recognize that in an ideal world where you do not have to deal with any performance issues, you don't need to store a read model at all, since you could simply derive it on demand. Similar considerations could also be found in the paper Out of the Tar Pit by Ben Mosley and Peter Marks. If you haven't read this paper yet, you should put it on the top of your reading list. Nevertheless, the event bus can also dispatch the events to other components of the system or other systems, which, for example, updates their database, sends emails, or performs any other side effects. So, now we know how the read models are updated and the events are dispatched by the event bus. But the events also have to be stored somewhere. In a CQRS architecture, this task is dedicated to the so-called event store. An event store can be realized as a normal database table where one record is stored for every event. The events inside the event store are the primary data source. All other state is just another view on this stream of events. In other words, it's derived from these events. The immutability of the events also offers some nice design options regarding the event store. Since an event will not be modified, the event store can be append only. There is no coordination involved when different parts of the system append events or read existing events from the event store. Consequently, the database for the event store doesn't need to have any special coordination capabilities like transactions, for example. So, an easy-to-scale, durable key-value store is sufficient as a good database for an event store. Last but not least, immutable data also offers the possibility to be cached, which is another good option to increase the overall performance of your system. This is also the case for the read models. Now we come to the command side that contains the heart of the application, the domain logic. It handles all write operations of the system and takes care that all conditions are kept. In our online shop scenario, this could be the condition that after checkout, the user should not be able to modify the contents of the corresponding shopping cart anymore. Write operations are expressed in the form of commands and instructs the system to perform an action like adding a product to a shopping cart. A command often contains almost the same data as the corresponding event. The difference between a command and an event is that the event has already happened, while the command is a pending operation which can be rejected, modified, or deferred by the system. So let's take a look at an example command. You see that the command, as I've already mentioned, contains the same data as the corresponding event. Here it's the shopping cart add event. So the question is, who should process this shopping cart add command, and what should be the boundary of this operation in which all the data is kept consistent? Therefore, a CQRS architecture usually leverages several ideas from the domain-driven design approach. Among other things, domain-driven design describes a concept which is called an aggregate. So this is a definition of an aggregate concept by the domain-driven design community. It's a complex construct to maintain an even more complex net of objects. So thankfully, through Clojure's simplicity and its time model, we can have a simple notion of an aggregate. So let's take a look at the way how the aggregate concept is implemented in the Eve library. An aggregate, this one is an aggregate, is merely a plain Clojure map, which of course can include nested maps or other data structures. The aggregate value is associated with the identity of the aggregate through the underscore aggregate entry here. The underscore position entry, POS entry, or rather position entry, is a simple counter which is incremented on every event that is issued on the aggregate. As I already mentioned in the introduction, the position is really essential, since it's stored inside the corresponding event and defines the causal order of the events, which have happened on the given identity, or rather aggregate here. The aggregate value is typically used to store the data which you need to protect the rules and constraints defined by the given aggregate or your domain which you are implementing. In other words, it's the data for your domain logic. So, in the case of a shopping cart, the aggregate value can be used to check, for example, if a given quantity of a product can be removed from the shopping cart without causing a negative quantity in the shopping cart. Therefore, the aggregate value on this slide tracks the quantities of the different products here under the items key. All this kind of checking is done by the so-called command handlers. A command handler is a function which receives the aggregate value and the command map as parameters. The result of a command handler is a sequence of events. So here you see on this slide a command handler for the shopping cart add command. The command handler receives the aggregate value or the current state of the aggregate and the given command as parameters, as I said. And here the command handler merely converts the command map into an event map. So it simply changed these two keys, which is a convention how the events and commands are marked in the if context. So, but normally the command handler implementation uses the current state of the aggregate to figure out which events should be returned. Naturally, the command handler can also decide to reject the handling of the given command by throwing an exception, like it would be the case in our aforementioned scenario, where otherwise a negative quantity in the shopping cart would be the result. The if library offers some convenience functions to implement command handlers and stick them together. Basically, command handlers can be combined in a similar fashion like the request handlers in the context of a Ring web application. So, the command handler has to figure out which events should be applied to the state of the aggregate. But which component in our CQRS architecture should modify the state of the aggregate? This leads us to the one part of the CQRS architecture which is still unexplained. This part takes care that the aggregate is loaded so that further commands can be processed on the aggregate. The name of this part, or rather concept, is repository, also from the domain-driven design things. In many CQRS implementations, the repository is compacted with the storage and coordination mechanism. In Eve, the mechanics of a repository are separated from these details. However, you still need some kind of coordination mechanism to handle the changes on an aggregate consistently. One possibility is to place the state of an aggregate inside a Clojure atom. But the core of Eve is not compacted with any coordination mechanism. So you're able to choose the technology which fits your application best. If you need to coordinate changes between multiple aggregates, you can leverage Clojure's SDM and place your aggregate inside a ref. Or you use about to coordinate changes on your aggregates between multiple nodes. The crazy thing here is that we also use the event sourcing technique to change the current state of an aggregate. Like in the read model situation, the current state of an aggregate is continuously updated by applying new events to it. For the implementation of the corresponding event handlers that build the current state of the aggregate, we can leverage the same event sourcing functions which we have already used on the read side. However, the data of an aggregate value is only used by the command handlers, or rather for write operations. Therefore, it is very different to the data which you typically would find in a read model. For that reason, I've decided to call the data of an aggregate value write model. Sometimes the write model of an aggregate is not loaded yet. So you need to receive it somehow. To load the write model of an aggregate, we simply use the events of the aggregate, which are stored inside our event store. So we still need some kind of handler that knows how to build and update the write model of our example aggregate. So here are two events which are processed on our shopping cart aggregate. Here we add 4 Clojure books, and afterwards the write model of the aggregate is this one. So we've captured that we have 4 Clojure books inside our shopping cart, and then we decide, okay, I only need 2 in the moment, so we remove 2 Clojure books again. So the write model is adapted to it, and now you only have 2 Clojure books inside your aggregate write model. So yeah, this is a little bit too large, this function. Doesn't matter. This is a so-called write model handler. It's the same like the read model handlers or event handlers as we've seen on the read side. And it simply do the housekeeping to track the current quantity of the products and stored here inside the aggregate write model. So that after the processing of these events, we receive the correct write models. So, with this information, we could reject a shopping cart remove command that tries to remove more items of a product as there are currently in the shopping cart. In this way, we would avoid the negative quantity, as I already mentioned. Last but not least, here's a possible version of the corresponding command handler, which does protect the aggregate from negative quantities. So, also a little bit large. So here the command handler, as I've said, also receives the current state of the aggregate, the command, and then he extracts the quantity and the product ID, and get the current quantity. And then he checks if it's okay when I remove 4 books from existing 2 in the shopping cart, and if there are too little books inside the shopping cart, here this command handler throws simply an exception which told the user that it's not enough books inside the Clojure, inside the shopping cart to perform this action. In a normal shopping cart or online shop implementation, you would of course handle this event more gracefully, so you can adapt the quantity inside the event and simply set the quantity to 0 or remove the product entirely. So, the if library. At the moment, the if library is really only a couple of convenience functions to realize event sourcing and CQRS and a CQRS architecture in Clojure. The talk already showed the main insights which was necessary to transfer the CQRS approach into the functional world of Clojure. These insights are the main assets of if. Regrettable, the preparations for this talk has consumed almost of my free time in the last couple of weeks, so there was only little time to extract if from our code base. However, the extraction is already done, but there is no documentation and no comprehensive example which shows how to use if. So I decided to release if in a couple of weeks when it's ready for the public. Nevertheless, if you are currently planning to realize a CQRS architecture in Clojure, come to me, talk to me, and we will figure out if a preview version of Eve can help you to fulfill your task. In any case, I will announce the first release of Eve on the Clojure mailing list. So that's it. Question? Thank you.